Maybe you remember the time of COVID, where people were monitored with an infrared sensor to measure their body temperature. That at least was helpful, but in case of a too high body temperature, the damage was already done, and not only for that person, but also for the people around. Therefore, it would be nice to have a system that can monitor this in an earlier stage. So the COVID tests were developed. This was basically an internal sensor, which we could read out afterwards. Unfortunately, for a battery pack, battery or cell, this is not that easy, but devices that can do this job are on the way, as we will see here, and not only for measuring temperature. So let's see why this sensing comes in the overall, call it battery loop. Once the battery has been fabricated, it will be tested for evaluation, and information can be uploaded for artificial intelligence to improve the battery eventually. So now the cell is ready to be purchased, and then the consumer would like to have a safe device. Since the battery will not have an endless life, there comes a point where it dies, or where it becomes dangerous by catching fire or worse. That point we would like to avoid, and therefore we would like to have understanding when the battery may reach that point. Thus, sensing the quality, the state of health of the battery needs to be measured and evaluated by proper diagnostics. If the battery is about to reach that point, the battery can hopefully self-heal, or the battery management system decides to stop it. Anyhow, measuring the relevant parameters for degradation is important. These parameters can be temperature, pressure, voltage, internal resistance or impedance, and absorption of radiation. So let's start with the temperature and pressure sensing. Accurate temperature measurements are of paramount importance to give feedback to the battery management system so as to maximize the performance and lifetime, but also to prevent dangerous situations. This is particularly challenging in the case of heavy thermal gradients developed inside batteries, which might quickly develop during operation. The traditional ones, such as thermistors, resistance temperature detectors, known as RTDs, or thermocouples, can be used for local surface or local temperature measurements in the pack. These methods are only for external use, but we would like to intervene earlier once things might go wrong. Therefore, internal sensing is important, and that means we must bring the sensors into the cells of the battery itself. It seems that several of the traditional methods can be adjusted for internal measurements too. Obviously, it is important that the battery cycle life and performance should not be affected. Also, the temperature measurement devices should be insensitive to the chemical environment of the battery materials, and the temperature measurement devices should be compatible with the assembly process. Apart from the traditional methods, pyroelectric and piezoelectric devices can be used to monitor the temperature and pressure as well. These sensors can be made very thin today and can be easily introduced in the laminate structure of the cell. A fiber Bragg grating temperature sensor based on deviation in infrared light transmission can even be made to measure temperatures at multiple locations. Unfortunately, the development of these devices for lithium-ion batteries is still in a very early stage. And like the pyroelectric and piezoelectric devices, they still need to be included in the assembling process. It would be great if there were methods that can be used to measure temperature, pressure, and degradation via an electrical way, making use of the already present wires. In that respect, there are two methods are under development. Impedance-based temperature measurements. Here the impedance is being measured at a small relevant number of frequency and compared to a calibrated standard as uploaded in the battery management system. Because the temperature is measured through the impedance, measurement delays are short. Moreover, the impedance can be advantageously used for measuring other states, such as state of charge and state of health. The other method involves a differential voltage technique. The differential voltage can be simply obtained by taking the derivative of the voltage with respect to the capacity. Usually, this analysis is used to examine phase transitions, deintercalation mechanisms, and aging phenomena, reflecting the state of health. Interesting enough, both methods are being related to the state of health, which often is governed with certain parasitic chemical reactions occurring in the cell. Here it would be nice to monitor the formation of the species as a result of the chemical reactions. There is an interesting method developed with, again, a fiber where these species are being absorbed, and thus the transmitting pathway will be deviated depending on which species is being absorbed. By proper calibrating the transmitted, reflected and absorbed light, the degradation reactions can be verified and adequate action can be taken by the battery management system.